Thank you. I think given the short time, you did very well. And thanks everyone for coming. Yes, my name is Shambhu. I'm at SLAG for about 10 years now. And it was my great pleasure to come here. And actually, I woke up where I usually wake up and was able to take a short flight, and I was here at 9 o'clock already. So, I will tell you first what is the talk about, and I will tell you, why we should do this, why the taxpayers' money should be invested, and then I will go to the detail of my talk. So I got a laser pointer, right? And I got solid targets, lots of solid targets. Right? Maybe we can do an experiment here, or maybe not. So I like transparent targets more, like glass. So the laser goes through. So my experiments are, imagine that if I had a way to crank up the power of this laser. So this has right now only about a milliwatt of power. If I had a way to crank up the power to many orders, right? And what would happen to the target that I'm focusing my laser to? That was the question. Right. So maybe I should ask, how many of you have used lasers and focused lasers to something?
I'm not an experimentalist, but I do the simulation. I know that like you will burn.
Good. There you go.
Right?
Yeah. Thank you. So you'll burn. You'll burn right through it, right? So that's I don't know if that is a problem for theorists, but certainly for experimentalists, if I burn my sample, I have to go home, right? So the way to get around to that is, if I can have a very short pulse laser, I can still put intense laser pulse into the sample, but without doing anything to the sample, without basically damaging the sample. So how can I do that? So what allows me to do that is this Nobel Prize winning technology of ultrafast lasers allows me to do just that. So here, this technique is called a chirp pulse amplification, which is a way to amplify the laser, not only make it really strong, but also keep the pulse really short in time. Okay, the idea was that if you want to amplify the laser pulse directly, then the intensity of the laser pulse in the amplifier goes up, and then you basically burn the amplifier, right? So instead, what you could do is you could make the pulse really long. You stretch the pulse in time, and then do the amplification. So that way, you keep the peak power density on the amplifier still low, but you can amplify by millions times. And then afterward, you put it together, you recompress the pulse, and you have the really short pulse. So this is a very high-level introduction of how the chirp pulse amplification system works. And this was recognized by the distinguished prize, of course. And lasers are just cool. Look at the picture, right? I mean, you can you get to wear cool glasses too. And of course, you don't have to wear a tie every day. But so the encouraging note perhaps to the students is that Dana was actually a student when she was working with Gerard, and they were awarded, both, including Dana, was awarded the Nobel Prize. So the hard work as a graduate student does pay off. Okay, so now, I can have my sample survives the strong laser field, right? There's the other interesting thing of this short pulse. We also called ultrafast. Short pulse, ultrafast. I don't know why we call this way, but short pulse in time, and since the pulse is short, it is fast as well, I guess. So the advantage of having ultra-fast pulses is just like in this photography, right? If you have fast moving subjects, then to be able to do the photography clearly, you need very fast shutter, very fast flash of light in the camera, so you can resolve this motion. So what we are interested on is on this ability of the ultra-fast lasers to be able to see really fast moving, small things move fast, okay? Like electrons move fast, much faster than the nucleus. So I'm showing here a few time scales. I wasn't sure whether you are familiar with all these units, so I have it here. So let's say if you have a picosecond pulse, then this time scale corresponds to the rotational time scale, typical rotational time scale of a molecule. And think about a nitrogen molecule that has 2 nitrogen atoms, and they rotate in this time scale. Okay. Similarly, the vibration of the molecule or the vibration of the lattice in solid systems occur in this femtosecond time scale, and the motion of this electron occurs in the attosecond, which is 10 to the minus 18th of a second, right? So we want to be able to visualize where electrons are, just for the illustrative purpose. But in reality, what we want to find out is the electron density in the system, and we'll talk more about that in a bit. So let's see what is the progress over the time in terms of the how short pulses have been available. So you can see here this Ti-sapphire laser technology really had this the first plunge in the pulse duration down to few femtoseconds level, and then came out this high harmonics, which we'll talk about a lot in this talk, that took another leap, okay, and brought a pulse duration of light, the laser, to attosecond range, and current limit is in the range of 50 attoseconds. I have to update this graph, and that's the limit. Currently, my thesis advisor holds that record, and he came out in the BBC News on the title that that said human-made shortest event or something like that. For the illustrative purpose, again, with such a short pulse, you could think about the ability to photograph the electron motion inside, let's say, for example, the classical electron motion inside a hydrogen atom, which takes about 150 attoseconds. Okay, so now I'm probably old enough to care about the electron motion in a hydrogen atom, but many of students in the audience are probably want to have something more fancy or more challenging applications of such a short pulse laser technology. So here is one example. So here, so this is the work from Ferenc Krause's group at MPQ, that they used short pulse laser to modulate the current, to produce current and modulate current in a piece of solid. They literally put an emitter and measure the current, and the data shows that there is you can produce current by the optical field, and you do that in a reversible way completely. The interesting thing is that since the current reverses as the laser pulse turns on and off every half cycle or turns around, this frequency, this is the optical frequency, right? So the implications are, perhaps, towards pushing the limit of, electronics to very high speed. Like, think about, so current technology is based on the transistor, right? It takes, picosecond or nanosecond time to turn the direction of the current in a transistor. So if you could do this with at the optical wavelengths, that could have a huge impact in signal processing and other applications. Okay, so with that motivation, I show you the outline of my detailed talk. So you will find out that I will start by being an atomic physicist, which was my PhD on. And during the talk, I will turn myself towards, and I will sound more like solid state physicist. And I will start by introducing you the strong field response in atomic systems. And then I will move to the case of crystals, where we basically bring atoms together and form a periodic array. And we are looking for the fundamentally different response in high density periodic systems. And lots of surprises you will see, including in two-dimensional materials. And towards the end, I will show you some potential opportunities and talk about the challenges that we have in the community. And one of the things that you could do, because these experiments are based on solid targets, and we don't damage the solid, right? That was I declared that in my first slide. So that has implications to Attosecond devices and such. Okay, so here's my team. At Stanford, I collaborate actually for a long time with the group of David Rees, and more recently with the group of Tony Hines. And these are the people who actually did the work, students and postdocs, whose pictures may appear in their corresponding contributions over the talk. We collaborate with the group of Zhenggu Chang and Mike Cheney at the University of Central Florida. Similarly, with the group of Pierre Agostini and Rudy Morrow at the Ohio State. Recently, we started a collaboration with the group of Eagle Brainer at Sandia. And some of the theory work we did together with the group of Medagard at LSU. Okay, so this is strong field physics 101. Okay, so you recognize this, right? So this is the bound electron, the Coulomb potential. The electron is bound inside an atom, let's say a hydrogen atom, right? And you require certain ionization threshold. So it is bound with certain energy. So you need, if you wanted to get this electron out to the continuum, you typically need a certain photon energy that is higher than this ionization potential of the electron. So we have the strong field from the laser, so which is here. That's the interaction term of the Hamiltonian. So in our case, we apply this field, and the field is strong in such a way that it almost completely distorts this Coulomb potential. Okay, so now some of you probably took quantum mechanics, that that now this barrier, the Coulomb barrier, is completely suppressed. So it means that this electron could actually tunnel through this barrier with some probability, right? So now you don't really need high enough photon energy to get this electron out in the continuum, but this electron tunnels through the barrier. And this is the beginning of the strong field physics. So this is where things begin. Okay, we talked, this is Attosecond science. So to do attosecond science, you need attosecond precision, you need a good starting clock, right? And this is it. This is good because this comes from the nonlinear. The response is nonlinear to the electric field of the laser, so that makes it very precise. We talk about this in more detail later on. So let's see what happens to this electron after it leaves the Coulomb potential, after it leaves the atom. Okay, so the same thing again in more graphical, more illustrative way, I guess. So this was worked out in the early 90s, and I should mention, if you are interested on this, old papers and relatively new reviews and such. So at the peak of the field, so this is my laser field, okay? So at the peak of the field, we said the barrier, the Coulomb barrier gets suppressed, and this electron tunnels out, right? We said this. Now, what happens next? So I give you a clue. So this laser cycle turns around, okay? So now the question is, what happens to the electron, right? So if we have undergraduate students in the audience, and this is F equal to ma, and the clue is the field turns around, okay? So if not, so let me tell you. So when the field turns around, the electron comes back, okay? The field turns around, the electron comes back, and this electron could find the exactly same ion that it came from. And when that happens, so this becomes really interesting, that the electron has acquired a significant amount of kinetic energy from the laser field, okay? And then this electron is coming back to the ion. The ion is huge compared to the electron, more than 1,000 times. The ion doesn't move. The electron is in high speed, but it comes back and it smacks at the ion, and the electron recombines to the ion. So all this energy that it acquired, the electron acquired from the laser field, has to go somewhere, right? And that comes out as the form of the high frequency radiation. And this occurs every half cycle of the laser field, okay? And to give you the time scale, so this laser field from this maxima to these other maxima is about 2-3 femtoseconds only. So this type of radiation that is coming out on this sub-cycle scale has to be much shorter than this total period, which is about 2-3 femtoseconds, right? So that's the beginning of the attosecond. That's the at very high level the idea of how these pulses are so short.
So the binding energy of the electron is on the order of 10 electron volts. So that means you need an incredibly large electric field in order to make this, happen.
You need a sufficient electric field.
How large is the electric field required?
So typically on the order of volt per angstrom is enough, because you don't have to completely suppress the barrier, because with some lowering of the barrier is sufficient for the electron to tunnel through. So if you had the enough intensity, you could completely suppress, and then electron could just go over the barrier, right?
The average tunneling time or the tunneling rate is apparently determined by the how large you
Yes.
suppress the potential, right?
Right.
But this is ultrafast process. So
Right.
I'm not sure if a slightly suppressed the potential can have the electron can have enough time to time on it. It's a WKB process.
Right. Yes. Yeah. So
It's pretty slow. I mean, if the barrier is not completely suppressed.
that's right. Yes. Yes. So what we are talking about is the time that we call the time it takes to tunnel. So the time at which the electron leaves the tunnel, right? So there is actually quite a lot of experimental work going on to actually measure this. So for relatively low field, the barrier is suppressed not as much, right? And the tunneling time is longer. But still, remember, so this is the suppression is every half cycle. So the time is still much shorter than the full cycle of the laser.
So can I say that the faster the light, then the stronger the electric field is required?
Yes.
Yes. Okay.
Yes. That's why, and if it is as fast as X-rays, it's very, very difficult to suppress the barrier. Okay. Yeah. Right. Right.
That's actually, I think the shortest pulse now is already sub 50 seconds. So how that's possible? This is the first question. The second one is like, so no matter how many periodicity you're doing for this one, only half of the cycle is accelerating the electrons. So it's also makes no sense why they have some high harmonic effect, like you accelerate for multiple up and goes. So
Right. Yeah. So yeah. So let me answer the second question first. Okay. As you said, I show only one cycle. In typical laser pulse, you have more like 20 cycles, right? And this emission occurs if you have 20 cycles, 20 times or maybe 40 times, because it occurs every half cycle. So what you measure in real, in the lab, which I will show you in the next slide, would be basically the Young's double slit interference. I mean, now here, we have two slits here, but when you have like 40 emissions, you basically have measured the interference of 40 emissions, right? And as a result, so this occurs every half cycle, T/2. T is the period of the laser field. So the Fourier transform of that is twice omega, right? And that's how you get a discrete fringes, if you like, in your interferogram, which you will see here. And this is what you measure in the lab. So what you're measuring here is the interference of this attosecond emission that occurs every half cycle, but your laser pulse has 20 or 40 cycles on it, and you measure this spectrum. Okay, so we'll probably come back to the first question. Okay, since I'm on this, so this is this is as you see this there is no graphical manipulation. This is how the experiment looks like. This is what I did when I was first or second year student. I shined a laser pulse into a gas target and then measured the spectrum of what comes out. My laser was 1.5 eV. The spectrum that I measured extended to up to 100 eV. Okay, and this was first done, of course, in the late 80s, and the underlying physics was understood as I described in the previous slide. And what I want to point out here for the future reference for future slides is that this highest energy that you measure is actually important. Okay, so here in the atomic case, this highest energy is basically given by how much kinetic energy that electron acquired in the acceleration, right? How much the kinetic energy that electron acquired, and that is given by simply by the this what we call the Ponromotive energy, which is the cycle averaged energy of the free electron. Free electron. Okay, I emphasize that free electron in the laser field, and that is proportional to the square of the laser field. Okay. Now this is how the experiment works. Now, what can you use this experiment for? A lot of applications. There is actually a huge range of research on this. I will show you only one example, which is that I'm actually highly fascinated by this application. Also, this was a good reading material when I was writing my thesis at the time. So this is the measurement of these harmonics from a aligned diatomic molecule, nitrogen molecule. So you can use the laser field to align the molecule, and since molecule is different from atom, atoms are spherically symmetric, molecules have different shapes. So in this case, depending on the shape, the angular response, the efficiency of the harmonics at different angle are very different. Okay, so Colloquium and his group use this anisotropic response of these individual molecules, and they were able to retrieve the participating electronic orbital, the HOMO orbital of the nitrogen molecule. Hopefully this matches to what you read in your quantum mechanics books. So in some sense, so this molecule sends an electron out in the laser field, and sort of like taking the selfie, right? So the picture, your picture when you're taking a selfie depends on how you take the selfie, right? Your camera is here, or if your camera is here, you see different things, right? Essentially that, and I was so impressed with this technique, and I started thinking about what you could do in the cases where you have not just a single molecule, but maybe array of atoms, right? So in the selfie language, what I'm asking is really, can you instead of taking selfie, can you take a selfie together with your girlfriend or boyfriend as well, right? Or even if I want to still push the language of selfie, can you take the selfie with your wife or husband, where you actually have legal relationship? That's exactly what is there in crystals and periodic systems. There is the phase relationship between different atomic sites, right? So these are the very naive, high-level questions that occurred to me, and we tried the first experiment. So we took a mid-infrared laser pulse and took a zinc oxide crystal, and we measured very similar to the previous gas phase experiment, measured what came out in the transmission. This is the measured data. So here you see harmonic spectrum, again, various harmonic peaks. But what was surprising to us is that we studied how this high energy cutoff scales as a function of the laser parameters. So in this case, it actually scaled linearly with respect to the electric field of the laser, as opposed to you expect the quadratic scaling in the atomic case. So immediately, we realized that there is something fundamentally different that is going on in high density periodic system, right? In addition to this recombination like channel, there must be something completely different, what we call block accelerations in textbooks, which is that essentially the electron runs in the periodic potential, and upon absence of scattering, this electron could radiate, and that photon energy could actually scale linearly to the applied electric field. So since this first experiment, there has been a lot of interest in the community, and ranging from ultrafast AMO to condensed matter physics, and there is a lot going on. And recently, David and I wrote a review article to summarize the progress, and this is available now in Nature Physics. So just want to point out here, there are several groups starting to use this harmonics to reconstruct the momentum-dependent band gap in semiconductors. We are interested to measure the valence electron distribution inside bulk. And this also gives a new avenue to look at the excited electrons in structures, and in interesting ways to control the strong field-driven processes by using engineered solid materials. And something I couldn't think about when I was doing the first experiment was ideas to even probe the quantum materials and interesting phase transitions with these methods. Of course, all of these applications require some level of understanding of the underlying mechanism. So I would like to take some time to tell you about the fundamental mechanism. You already saw this, the real space picture. So now I will switch towards and try to use the solid state physics language. So this is my momentum space representation of this model that you saw in the atomic system. In the solid, you have valence band and conduction band, and you of course have this recombination channel, which is recombining this conduction band with the valence band. I will tell you a little more detail about this in next slide. But in addition to this recombination, you could have this the block acceleration part. Basically, this electron runs in this conduction band, and if the band has an harmonic shape, and then the current becomes nonlinear, and it radiates, and the radiation becomes since you do this in multi-cycle, similar to the gas phase, you measure the harmonics. So there are at least two important channels. Okay, let's look at these channels in more detail, just to get everyone on the same page. So this is one channel again with more detail. What is happening is that originally I have an insulator. I have some electrons in the valence band, nothing in the conduction band. My laser pulse comes in and excites the electron. The electron tunnels to the conduction band, and the electron still experiences strong, and there is a hole, right? And the electron still experiences a strong electric field of the laser and moves in the band like that. The hole does similarly, and at certain time, this electron could recombine to this hole and give rise to this energy difference could come out as the high energy photon. So that's one channel. Okay. So you can already see that if you understand this channel well, you could maybe probe this shape of this band, or at least the momentum dependent band gap between in these systems. So the other channel was this block accelerations, right, which is basically you have an electron in the conduction band already, for example, and depending on the enharmonicity of this band, the radiated spectrum could be very, very different. To show you one example, so here I had two very slightly different bands, the green and blue. They are slightly different, right? But the calculated spectrum of harmonics are very different. So the idea is that by measuring the harmonic spectrum, perhaps you may be able to measure the band structure. Of course, now since we have these two channels, they compete, and we need to separate these channels so we can use them appropriately. These channels, interestingly, have seem to have two different temporal profile in the harmonics. This is to remind you what happens in the atomic case. Basically, the electron is coming back to recombine to the hole, and different energy electron comes back at different times. So different energy harmonic emit at different phase of the laser. This is called the dipole phase. And in the solid, in one mechanism is very similar to the gas. As I told you, and this has a chirp similar to here. Here it is shown in many more cycles than that. And the other channel is pretty flat. So here the emission phase of harmonics, so there is no chirp. So everything comes out at a fixed time. So this could give a clue to separate these two channels, right? So this is actually a difficult experiment because this time scale, we are talking about the attosecond time scales. So since absolute measurements are difficult, we went ahead and tried a relative measurement. So I will take a few slides here to describe you what the experiment is. So this is the relative measurement. We we split the laser beam into two identical spots, and we have them producing harmonics in the crystal at two different places, such that the laser field, the laser spot do not overlap, but the harmonics they are produced, they overlap in the far field. So we essentially do the interferometry. Now, when we have this, by the way, this has just come out in Nature Photonics, and the measurement is like this. So two laser spots far apart, right? And we measure the harmonics. So these are the harmonic spectrum, harmonic orders. And because of this interference of these two beams in the far field, there is a nice fringe pattern going up and down. Okay, so basically, again, Young's double slit experiment, and you're measuring the interferograph of harmonics from these two different sources. This is the starting point. Now, we change slightly the relative intensity between these two sources, and basically watch how fringes move. What we expect, the first thing is that when we increase the intensity on the laser field, we expect that this harmonic emission time move early in the time. This is how it is. So actually very nice. It's easy to understand that, you know, if you have a ramp connecting different energy levels inside solids, if you have a stronger field, then this ramp, you can excite electrons to higher states much faster in time, right? So basically saying that with the stronger field, the emission time of harmonics should arrive early in the pulse. Okay, but what we measure is actually different. So in this picture, the early is top, so harmonics are actually moving down, as we change the relative intensity, they were moving down. I will show you our calculation results by the amount. The direction is completely wrong, but also the amount is much more than what we expect. So to find out the reason for this, we did the same experiment, but in reflection geometry, which is here. So the setup is essentially the same, but we measure the harmonics instead of transmission in the reflection geometry. Okay, this is the measured spectrum, where you again see these nice fringes. Some smart students may already see the difference here, but what I want to point out to you is that now these fringes actually move up. Okay, and they move up very slightly compared to what we saw here. So what is going on is that the difference of this reflection geometry is that here, as I draw, these harmonics are produced only at the first 10 nanometer of the distance, such that the intense laser pulse did not actually have to propagate through the bulk of the sample. So here the laser pulse propagated had to propagate through the 200 micron thick sample, and the intensity of the laser is high. So the fundamental pulse accumulates significant nonlinear phase, and that adds into the generation process and makes things very complicated. Okay, so this is very detailed slides to show just that, and I'm going to skip just a nice graphics that even the division of condensed matter physics likes. I guess now I'm probably officially a condensed matter physicist. Okay, so what I want to also show you is a different experiment where I showed you early on the angular response of the nitrogen molecule, right? So I want to do the same experiment in crystals here. So this is my crystal magnesium oxide, and this experiment is very simple. I shine the laser pulse into the crystal, and I basically rotate the laser, either rotate the laser or rotate the crystal, and watch how the harmonic spectrum changes. Very similar to the nitrogen experiment, except here I don't have to align, I can literally align my crystal by hand. Okay, So also note that magnesium oxide is a cubic crystal and very isotropic, dielectric. The linear dielectric properties are completely isotropic, and even nonlinear properties like chi3 are fairly isotropic. So it was actually remarkable to see the very strongly anisotropic response from such a fairly isotropic system. There is no birefringence or anything. So if you look at this carefully, you will see that the intensity is, you have the intense emission along the cubic direction of the crystal. Okay? And there is a secondary maxima along the diagonal direction of the crystal. So our understanding to this anisotropy is following. We basically have a three-step process where we draw the electron trajectory inside the crystal, and let's say we start from an oxygen atom, because you have to start from somewhere. The same thing repeats every lattice, and and these are the electron trajectories for different laser polarization directions, and it is showing us that as you for example, in this direction, these trajectories connect these different atoms, oxygen and magnesium, and this is where we measure the highest intensity along these directions. And on the diagonal directions, they connect the same type of atom, like oxygen, and there is that corresponds to this secondary maximum in the data. And there are some trajectories where up to some lattice distance they don't really see anything, and that corresponds to this minima. So of course this is somewhat naive argument, but we can do better by taking advantage of the polarization of the laser field. We change the laser polarization from linear to circular field. So by changing the polarization of the laser from linear to circular in small steps, we can basically ask these electron trajectories to bend. And for a fully circular laser field, the electron trajectory goes like this, in helix. So as you see here, of course, the linearly polarized trajectory connects here to many different atoms that corresponds to the maximum signal in the measured data. And when the trajectory misses the atoms, there is the minima. And when the trajectories are bent enough, they start to recollide to the next nearest neighbor. Then you see the secondary maxima. So the idea, we can do lots of experiment like this in different crystal orientation and such. So the idea is that when the strong field driven electron intercepts to the first nearest neighbor atom, it produces intense signal. When it intercepts to the second nearest neighbor, it produces the second maxima. And if it doesn't intercept any atoms, it corresponds to the minima. So that's the model. And using this model, you could even retrieve the valence charge electron, which I don't have time to go into detail, but I can tell you why this is important. So valence charge density is important because these valence electrons are essentially glue which connects two or many atoms together and form solid, right? So you want to know what type of glue you have, a super glue or school glue or whatnot, right? So the idea is that if you have a way to probe the valence electron density, you would know chemistry. So valence electrons define the chemistry. So that's why this has implications. So before I run out of time, I will maybe just jump to the final slide. Almost final, which is this is the ongoing work that we are pursuing at the moment, which is to do something similar, but we want to take advantage of the noble electronic properties of solid state systems. So this is one example, which is, many of you may recognize these systems as a topological material where these bands have Dirac-like bands. There is no band gap, and there is this would potentially give us a new way to control these driven dynamics inside solid state systems. And this is very preliminary. Harmonics are produced from these two different materials. Hopefully, this simulates some discussion afterward, and I'm also here tomorrow if you will be interested to talk to me. So here I summarize my talk. So I assume so what time we have to close? Do we have more time?
Yeah, plenty of time.
Oh, really? Okay, then I could maybe show before I close. Then so maybe I take 10 minutes. My PowerPoint was already showing 16 minutes. So maybe I will show you this 2D work. Okay, so another example is how can you control these strong field processes by taking advantage of these these solid state systems. So here, so we took a single layer of MOS2 and we compared the harmonic generation process from a single layer with the bulk. Okay, so I want to point out that in the bulk, the arrangement of these atoms, molybdenum and sulfide, it's such that in bulk there is reflection symmetry. Okay, so the left is the image of the right. In the single layer, there is no reflection symmetry on this plane, right? So the left is different from right. So this was a very interesting way for us to recognize when we have the single layer sample. So as we do that by looking at the spectrum. Since you did not have a reflection symmetry, we measure both even and odd harmonics. When you had the reflection symmetry, because of this symmetry, the even harmonics cancel to each other, and we only see the odd harmonics. So this was a very, very good way to find out where the single layers are. For those who are working on these systems, know the difficulty of finding these single layers. So this was nice, but there was at least two surprises that we found out. So one was that we compared the per layer efficiency of harmonics, and we found out that the per layer efficiency on isolated single layer is much higher than that in the bulk. Okay. The other surprising thing we found out is about the polarization. So this is the measurement. So here we are measuring the polarization of harmonics in a way that the detector is polarized in the same direction as the polarization of the fundamental laser. Okay, parallel polarization. And we rotate the crystal, and of course the crystal has this nice 60-degree rotation, and we reproduce that. But the surprise was this. So as you might already see, in this parallel configuration, the odd harmonics are intense, and there is almost no even harmonics, right? In the perpendicular configuration, we see mostly even harmonics, so no odd harmonics. So typically in atomic experiments, all the harmonics, atomic HHG experiments, harmonics are always polarized to the polarization direction of the laser field. And this is a surprise that in single layer system, the polarization is actually orthogonal to the fundamental laser field. Okay, and also I think this is a very fascinating nonlinear optics experiment, because I mean the thickness of this material is only 0.5 nanometer. Okay, you have a system where you send in a laser pulse of certain frequency, and it interacts with only 0.5 nanometer of material, and the frequency of the laser changes to like 13 other new frequencies, and I think this is really fascinating. And one of the possibilities why we could have this such a orthogonal polarization on the harmonics is from the contribution from the Berry phase. So this is the velocity, group velocity of the electron in a band, right? And usually, as I told you earlier, the electron runs in a band, and when this motion becomes nonlinear, and it radiates the harmonics. The harmonics are polarized in the same direction as the laser field. Okay, so usually there is also the another term in the equation, which has this Berry phase, but usually this is neglected because the typical electric field in typical experiments is sufficiently low, and in our case we have a gigantic laser field, and this contribution becomes as strong as the contribution from this term. And I forgot to mention that this, because of this cross term, this acts as a magnetic field, just like in Hall effect, that the electron produces the anomalous current in the orthogonal direction. So if you just look at the band structure, this single layer band structure is not very different from the band structure of the bulk for us, considering we're talking about very non-resonant process. So that's the difference. What is really different is this is the Berry curvature that is plotted over the same range of the band structure, and you can see that when you're looking at this k point in the momentum space and k prime point, this Berry curvature changes the direction. Okay, and because of that, you have this this term coming into play. If this was same direction, the total effect would be 0. Yeah, so now since I have time, as it turned out, I will show you briefly another experiment. So this is actually very recent, the experiment together with the group of Eagle Bernard at Sandia. So this is a heterostructure. Okay, some of you may know this is an interesting material called epsilon near 0 system, which is basically that you have these different materials putting together in a way that the total dielectric constant becomes 0, close to 0. Okay, so because of that, you form a you form essentially a cavity, if you like, between these interfaces, and that enhances this local field inside the cavity. And because of this enhancement, these are calculation results for particular polarization direction. We expect that the field is local field is enhanced by in the intensity by factor of 20 or such, and we observe in the experiment by measuring harmonics. So only in p polarization, where we expect the enhancement, we measure high order harmonics, and in the other polarization, we don't measure harmonics, high enough harmonics. So this is just to give you an example that because we can produce high harmonics from solid state systems, this allows us to explore many opportunities even in heterostructures to measure the these noble dielectric properties of these materials, and even understand how these plasmonic resonances and enhancement actually work. So let me just show you the last experiment then, before closing. So this is a direct comparison between gas and solid. Some of you might find interesting. So the comparison was, the purpose was pretty obvious, right? So I talked about the harmonic generation process in atomic systems, and I talked about the same thing in the solid, but the solids had surprises. So we wanted to do a careful study where we could compare directly gas and solid. The most direct way we could do this is by, not the easiest, but by doing experiment in solid argon, since the gas argon experiments were done previously and understood for a long time. So this is a difficult, technically challenging experiment, but when you find talented graduate students, and they can make anything possible. So this is the sample that George prepares. So what you are looking at is the Newton's ring off of the solid argon. Because the solid argon has different thickness, you see this nice Newton ring, and he shines the strong laser field through this and measures the harmonics. So these are the harmonics. This is the raw data, and what he finds out is that because now, without changing any laser parameters, he changes from solid to gas and solid and vice versa. Right. So he found out that so here he wasn't just talking about one harmonic being slightly more intense in solid compared to gas or anything. So he finds out something spectacular, which is that when he puts the gas target, the harmonics extend to only to certain harmonic energy, like 27th harmonic. And this entirely new thing he sees only from solids. A completely new plateau feature appears only in solid phase, even this is actually a big deal because even in rare gas solids, so rare gas solids is a pretty lousy system. So these atoms are basically put together simply by van der Waals forces, because right, argon atom has all the outer shell is all occupied with the electrons, right? So it doesn't want to interact with the other atom. So when you form solid, these atoms are basically sitting together like soccer balls sitting on top of each other. Okay, so even in such a weakly bound system, we see this remarkable difference in the strong field response. And I think that is really spectacular, and we are still investigating the details of it, and lots of experiments are coming forward, and lots of theory work as well, but there are limited predictive theories, and I think that the entire field is very exciting. So I would like to now really summarize the talk. Okay, so what I told you today so far. I showed you the first observation of high harmonics from bulk crystals. So that was done in a zinc oxide crystal. And then since then we have observed a string of surprises, especially on the mechanism of the harmonic generation process on different systems, and I showed you the novel observation of the novel solid state effects, such as measuring harmonics in completely orthogonal polarization direction, and I showed you one example of how we try to characterize harmonics by referencing one harmonic beam with respect to the other harmonic beam, And the difficulty is because of the attosecond timescales, but these relative measurements also provide very useful information. I showed you our model to understand the crystal orientation dependent response of in magnesium oxide crystals, where we essentially draw very similar to the gas phase the real space electron trajectory, and be able to describe more than qualitatively the anisotropy that we measure in the experiment. And if you noted this, that the electron did not actually have to go back to the same ion that it came from. That was actually pretty conclusive, because in the circularly polarized field, the electron never goes back exactly. It moves in helix. So that was also a fundamentally different response that we observe in dense system like crystals. I think the future is bright, and hopefully this was some of this was interesting to you. With that, I thank you for your attention.
Shambhu. So are there any questions?
Can you show me the slide of the Mary curvature?
Yeah.
Okay, so the Mary curvature is on opposite side of it's like K and K value.
All right, K and K prime.
Yeah, so does that mean that K and K value, K and K prime value electrons are subject to opposite anomalous velocity, so that you have a value Hall effect?
Right.
Okay.
Yeah. So
how can you resolve the value degree of freedom?
so we have to you have.
You can easily resolve the spin degree of freedom, but for the value degree of freedom, how can you resolve it?
Right. So the linearly polarized experiment cannot resolve. What we want to do next is we come in with circularly polarized pump left and right, and that will be sensitive to different K and K prime because of the different helicity. So that experiment will show the difference.
Okay, so the orbital degree of freedom are also on the opposite side. So I mean the angular momentum of the orbital angular momentum of the electron from the two valence are also opposite to each other.
That I'm not sure. I have to think about it. Maybe we can discuss more. But certainly, the proposal, the pending proposal, is to use different helicity and populate different helicity on the pump to populate K and K prime, and then we come in with a strong field and produce harmonics, and then we do difference experiment. Okay, so here.
Actually, it's excellent results. I have to be honest, I have plenty of questions.
Sure.
Compared to solid before. So I totally understand this is very difficult experiment, and you got very good nice result. But my question focus on the model. So explain all the things. So could you please go back to the you call it 3 steps from the interband excitation
Okay.
and the separating interband and then comes back to the condition. That one. Yeah. So I think we have maybe kind of 3 small questions about this.
Yeah.
So first of all, I think the photon energy you use to decide the electrons crossing the band gap is way below the energy of the band gap, right?
Right.
So using kind of far infrared
Yeah.
to do this way. So it needs maybe several photons to pump the electron from the valence band to conduction band.
10.
Yeah, right. 10 maybe 10.
Right.
So if this one's like the conduction band is like kind of 1 with the electric field as the left-hand figures, you should have some kind of how to say slope, kind of across along the electric field. So it goes like maybe we also call Frankfurt, Frankfurt
Right.
effect or something like this. So it's like the bandstructure is never be this kind of symmetric way. It goes to like slope over. So that may give you some tunneling. So that's kind of one how to say image or picture. One kind of picture. Another one is like, okay, we treat all this bandstructure as a phase, and then you use some kind of like multi-photon process to pump the electron out to this. So yeah, so how can we define the interband and intraband thing? So because this totally equal to each other, these two pictures.
Yeah, so the question was, so you have two sources of radiation. One is the intraband current, which is the driven electron motion in a single band, right? The other channel is the recombination-like channel. So how do you distinguish between these two channels, right?
Yeah, exactly. The interband current is actually can be directly detected or measured in experiments.
No, right. So, so what they measured, I showed in the previous this Ferenc Krause's experiment, is they measure some current, right? Yeah. So that current is maybe dominated by the right. Yeah. It's difficult. So our proposal to distinguish between these two processes is by measuring the emission time of the harmonic. So in this recombination case, maybe I didn't explain this clear enough. I thought we were running out of time for some reason. My PowerPoint was going faster. No, it's okay. So this is when we this acceleration in this recombination model. So this harmonic comes out at this time, right? The other harmonic, let's say if I drew another line here, lower order harmonics, that harmonic comes out earlier in time, right? Because the electron has reached at this place much earlier than here. So if you can measure the emission time of harmonics, then you can, if there is a delay between different harmonics, then you know that this is the channel. Now in the other case, which is the single band driven electron current, so in this case, whenever there is strong enharmonicity in the band, so all the radiation, almost all the radiation comes out exactly there. So there is one trajectory. Okay, let me make this clear. In the previous case, there were several trajectories. This is one trajectory, and there is another trajectory, another trajectories. Okay, so here the electron trajectory is a single trajectory that radiates different energy, just like the electron in the synchrotron runs around. A single electron runs in one trajectory, but radiates different energy. Okay, so just like that here. So different energy, they all come out exactly at the same time. So if you were able to measure the emission phase, this is the all calculations. So if you find out the emission phase and they are coming out at the same time, then you know that the source is the single band intraband, right? If you find out this, then it would be from the two band, right? So we haven't done that measurement. What we did is a self-referenced measurement, and the result, which I went quickly, was that so the theory said that when you so this is a relative measurement. Okay, I'm showing here the time frequency profile of harmonics. For one intensity, there is certain emission time. When you increase the intensity of the laser, this harmonic comes early in time, right? We talked about that. So this is one channel, and when this happens, if you're measuring the fringe shift, we know the direction which way the fringes go, right? So this is what you expected. This is all theory. If this was from the other channel, the single band channel, then everything comes out at the same time, doesn't matter what the field is. So there you would expect no fringe shift. Okay? So this is the data. So that's the theory, that's the data. So what we measured in the reflection is very similar to what we calculated. So in the magnesium oxide crystal, from this relative measurement, our results are consistent to this two-band model.
So that means the interband power.
Yes. Right.
Okay. So I covered to that.
Oh, okay.
So it's about the space. You give a very simple model of this kind of the space symmetry of the symmetry of the lattice. Give something like the angle, angle resolution of your harmonic nervous signals. So for that one, I think this could work fine for some, you mentioned the zinc oxide or something. But for the MOS2, I think it's different story because sometimes suddenly you have to take care of the band structure topology, even the valley, the valley degree, and all those are maybe kind of so-called valley-tronic things. So that means maybe it's kind of you mentioned the final is like the real space trajectory could also work here in the solid, but actually in the solid, in the condensed matter physics or solid state physics language, it should be band structure all the time. So maybe even though your lattice has some symmetry, but your band structure may have lower or higher symmetry.
Right.
So I think maybe kind of you have to move to the real space trajectory to kind of a reciprocal space trajectory or something. So this is one comment. The question is, have you ever measured the angle map, the polar map of the MOS2 case, the high harmonic generation, like the angle?
Maybe unless you have a quick answer to that.
Yes, I do. So yeah. So the quick answer is that so real space was transformed into the momentum space calculations, and MGO, they also produce very similar results.
Okay, so let's thank Shambhu again.
Thank you.